Hello, hello. Okay. So you can hear me in the back, right? Yeah. Okay. Shall we start? Okay. So we'll get started. So so what and all we covered, I just want to remind you all. So let's just look at, yeah. So these are three. So today in the afternoon session for the lab, you will begin with trying to do back propagation for a simple neural network. Then you will do k-means followed by elbow method. So k-means followed by elbow method, and k-means also you can implement from scratch if you wish. Okay, so it's up to you. And followed by trying to study how multivariate Gaussians look for different values of sigma. That forms your third thing, just to study how multivariates look. So fourth is related to what I was talking about, EM algorithm. So let me tell what you need to do. But before that, so what we saw is that we went through a whole lot of derivations. We tried to, for the missing information case, right? We really don't know what is the cluster center. We came up with this formulation. Okay. So here the problem is pi k, mu j, and sigma j squared depend upon gamma. So let me just say this is called as gamma. Okay. So this is a Greek alphabet. Similarly, this is mu and this is sigma. I mean, I should have told you probably earlier, but anyway, so this is, of course, you know this is pi. Okay. So what the problem is, pi, mu, and sigma square, they depend upon gamma ij, and gamma ij depends upon pi, mu, and sigma square. Okay. So even if you didn't understand all the calculations that we did prior, but this is what we ultimately came to. You do a whole lot of calculations and you arrived at this. Okay. So now what is the EM algorithm for Gaussian mixture models? So let me write that. Okay. So what you will do is, so first step, init pick pi, mu, sigma squared. So this pi is like pi 1, pi 2, pi k. Similarly, mu 1, mu 2, mu k, sigma 1, sigma 2, sigma k. Pick this randomly. Okay, then loop. So this is pi 0, right? Pi 0, mu 0, sigma 0. So loop till convergence. So again, you will ask me what is the meaning of convergence? Same idea that is there in EM. Sorry, that's there in k-means, that your cluster centers don't change a lot. So what will you do? So you will do computation of sigma ij. Sigma ij is pi j fj divided by summation pi c fc, sum over all c. So this is the first. So this is the step t plus 1. So you will use whatever is available in step t. Okay, this is the E step, and your M step is you will keep sigma ij fixed and you will compute these three, right? So pi k t plus 1 is equal to basically this sigma I summation sigma I k t plus 1 divided by whatever that is n. Similarly, mu k t plus 1 is equal to sigma I k t plus 1 times xi by summation sigma I k t plus 1, and finally sigma j t plus 1 So, okay, so what you will do is you will get, you will first fix mu, sigma, you'll first fix these three parameters, pi, mu and sigma, and then you will do E step, okay, and then you'll compute gamma ij. Then using that gamma ij, you will do this, okay. So this is the simple algorithm, nothing else. You keep one fixed, vary the others, then you vary the others, then keep the other one fixed, like that. So this, if you do, this is called as alternate maximization, right? So this procedure has a theoretical guarantee that it will converge to a local optima. Okay, there is a guarantee, but that unfortunately is too much beyond the scope of this class, but you can read up at a later point. So what I would like to say is, like, there is always, for machine learning, there is always the black box view, right? You always use sklearn or whatever, like all these libraries, and you get some things working, but you should also understand what drives these operations. So you should also get white box view. Okay, so both these views are essential if you really need to learn the subject well. So to start with, it's fine to use black box machine learning. You understand the how it performs in various data sets, but at some point you need to go and look at the finer details. Okay, and it is kind of scary, but you should persist, then it will be good. Yeah. So black box just means you don't have any clue how it works. You know what input it takes, what output it takes. You just run it. You put the data, you throw the data, you run it, you get some output. If it's not happy, you change the model, perhaps restart the machine, have a coffee, come back, try something else, right? White boxes, you truly try to understand what is the internal, why it works, try to use something sensibly, right? Make good guesses. So black box works. It's like people are able to get by just by understanding the black box, but at some point you should put an effort and try to see the math as well. Okay, it's not too difficult. Initial hurdle, if you're able to cross, it will be fine. Okay, so I would just like to contrast this with k-means. Okay, so can someone help me write k-means over here? Yeah, so what do you do first in k-means? Yeah, so you choose the cluster centers, right? So choose centroid, choose mu1 0 to mu2 0, like this, at random. Okay, at random from your data set, right? Then loop till convergence. Then what do? You compute Zij, right? Do you remember this? So you will compute Zij equal to 1 if the distance between xi minus mu j is less than or equal to, for all other points, xi minus mu k. So whichever is the closest point to the current point, you will set Zij equal to 1, correct? And what happens in the next step? You just compute mu j, right? So that is mu j of t plus 1 is equal to Zij of t plus 1. So this is t plus 1 xi by. So can you see some contrast between the two, right? So is the idea clear? So Zij of t plus 1 is either 1 or 0. It's a hard assignment. Okay, so you are either assigning ith point to one of the k clusters. There has to be a minimum, right? If there are k fixed values, there has to be a minimum. One of them is assigned 1. But here you are having a probabilistic assignment. Gamma ij is a probabilistic assignment. Okay, do you see the difference? And then here there is no computation of pi and all these guys. You don't compute pi, k, t plus 1, etc. Somebody is asking a question. Okay, so yeah, so this is the difference. So this is called as so let me write it in a different color. This is hard assignment. Okay, so homework 4 or assignment 4 for today. So there is one more which the TS have prepared, a few assignments, but if I think one of this is quite similar to what they have prepared. So it's just this. So before that, here, so there is a small change we can do. So this particular clustering we have done assuming that the dimension is 1. Okay, so mu k is a single dimensional vector, x is a single dimensional vector. So what I'm saying is we looked at a case where there were just 3 groups, right? Income groups and 3 heights. We looked at this case. Remember, this is how we derived this. But in general, we would like to have these kind of shapes, correct? So these kind of shapes can happen in our clusters. So there will be only a single change. I will leave you to think about it. So gamma t plus 1 will be summation xi minus mu k gamma. Just a second. Xi minus this one, xi minus mu k transpose by gamma ik t plus 1 gamma ik t plus 1. Okay, so this is yeah, so this you can do. I think this will not be, this will be a problem, so you have to do this, I think. Okay, yeah. So if you do this, you can get this kind of arbitrary shape. So just check in Wikipedia. I mean, I might have made some mistake here, but please look at Wikipedia for this update. I think this is correct. But so, okay, so what is your assignment? So your assignment is to generate 3 different Gaussians like this. Step 1, generate this figure, right? So generate points with 3 different Gaussians like this. Step 2 is like use Gaussian mixture model and learn the parameters. Okay, so to generate this, you have to assume the parameters. So assume parameters here and forget it. So what is the meaning of this? See, you have a system. Okay, the system is like you put something, you get something out, and using the output you may want to figure out what is the input that was given, right? So it's like somebody has a disease, you give a medicine and then you see what's the output, right? So but what disease is there later you will not know. So what I'm trying to say is you assume parameters, get these values, then look at the values only and see whether you can get the parameters back. Do you see the point? So it is there are plenty of applications which use GMM, but for now, for you to understand, we are just going to make you generate and then try to learn those parameters. Okay, so this is going to be your assignment 4. All right. So are there any questions on EM? You have a question? No? Okay. All right. So then if there are no questions, then let us start the next topic, which is kind of easier, but little bit lot of notations are there. So I have brought some lecture notes to help me, which is called as decision trees. Okay. So okay, so it's like this. So decision trees is again both classification as well as a regression. You can use it for both classification as well as regression. And this algorithm is kind of does well, and it is easy to understand, easy to interpret. Okay, so here is how it works. So typically, right, so if you look at let's say you want to assign somebody into one of the classes, right? So basically, let's say you want to put first class, second class, that kind of a tree. You want to classify people into these kind of baskets. So what you will do is you will look at okay, what happened? Oh, okay, good. So you look at the marks. If it is greater than 75, you will have one label, right? So this label is first class with distinction, something like that, right? I don't know. So then if the marks is less than 60, then you do something else. But on this side, you will give first class. Then you will look at X is less than, I don't know, 50. Then you have second class. And then if something like this, right? So if X is less than 35, you say fail, or otherwise you say pass, right? So these kind of decision, this is a decision tree. So at every path you have different choices, and you decide one of the things, right? So this could be one way in which you can label a particular task. Similarly, even for medicine, you may want to do something like this. You look at blood pressure, you go, if it's beyond certain limit, then you will look at heart rate. Then if that is also beyond certain, so you can have a decision tree like this, and then at the end of the nodes you will have some decision, whether it's pass fail, it could be one example, or you can have even regression. So you may want to say about house prices, if based on various features, what is the house price of certain thing, right? Like that you can have. So this is a decision tree. Okay, so it's a binary decision tree, and there is a split. So depending upon some value, either you go here or that side. So there's a split. Okay, so here I have shown you a decision tree with just one feature, but in general there could be many features. Okay, so what is the problem with the decision tree? I mean, easy to see. What's the issue? I mean, not problem, but what's the main question that is here, right? So what variable to choose? Because in general, there will be more than one features, right? So which variable to split on? And the second question is what value to split on? What value to split? Okay, so these are the two questions that you need to be able to answer. And the goal of this is you want to do something, right? So first, so let's look at decision tree for regression. Okay, before that, so far everything is clear with decision tree, right? Any no confusions? Okay, so let's look at a decision tree of this form. So this is so you have x1, x2. So this is taken from by the way, whatever I am referring is the book. A good reference for this is an introduction to statistical learning by the famous authors Witten, SD, and Ibishirani. This book is available for free for download, so you can always read this. So there is a good chapter on decision tree. Okay, so you have this, and I will say, let's say I have this. So when I draw a line like this, that means what is happening? So I am splitting on x1. Is that okay? So the value that I have chosen is t1. So the first decision is x1 less than t1. Okay. So if x1 is less than t1, I may then perhaps have a split on x2. So this is let's say t2. So this is x2 is less than t2. I just want to show that a decision tree in general partitions the entire space into different segments. Okay, so this is this. So how can I get a line like this? Suppose this is T3. How will I get T3? Where should I put T3 in my decision tree? Over here, right?
T3 will split, yeah.
Yeah, okay. So this will be x1 is less than T3. Okay, so if x1 is less than T3, so this region, let me even, so again, this is from this book. So this is R1. So, okay, so this is R1, R2. So this region, I'm going to call it as R3. And if it is greater than T3, I want to do something like this. So let me just undo this. Say something like this. Okay, so this is T4. So how do I get this R4 and R5? X2? Yeah, correct. So X2 is less than T4. That is going to be R4. And if it is greater, then it is R5. Okay, so point is, when you take two features like this, and if you apply a decision tree, it will give you a partition like this. Okay, so typically we are only considering binary trees, and we are only having straight line splits. The decisions are always straight line splits. So that itself gives good performance. Okay, so yeah, so this is a decision tree. And for regression, what you do is for every region, so you will have a value like this. For every region, my final prediction f of x will be, so let's say I have defined m regions, 1 to capital M. So it will be CM indicator x belongs to RM. So what is RM? Like this, R1, R2, R3. So for every region, I will fix a value. Okay, is that all right? So what should be my goal? What should I minimize? So if it's a regression problem, somebody was saying in the, you have to minimize the least mean square error, right? For regression.
Error sum of square.
Yeah, correct. So what we need to do is you need to minimize. So you need to minimize y minus f of x whole squared. Okay, this you need to minimize. We need to minimize over c's and r's. You need to define different values of c's, different values of r's to minimize. Do you understand? So you need to choose m regions. You need to choose CMs. These are the things that are not known to you. So you want to do that in such a way that this error is minimized. So you have seen this error before, right? In linear regression. Yes. So by the way, so if there are multiple points, obviously there will be yi, xi summation. Okay. So suppose if I if RMs are fixed. So how do you choose the CM? How do I choose CM? Suppose if I do this, RMs I fix, somehow tells you that I tell you that the regions are fixed. So how do I fix CM?
Average of the,
yeah. So yes, so you just look at the average value in that region. Okay, so basically CM will be equal to average over all the yi's such that the ith point, xith point belongs to region I. Okay, so this is going to be my estimate for CI. Okay. Sorry. Okay. So first Did you follow this? How this what a decision tree gives you? It divides it into pieces. Did you follow that? So what the decision tree for regression does is that for every region, I want to fix one value. For every region, I have to fix one value. And the way I fix that value is so as to minimize this error. Okay. So there are two things that we need to do, right? You need to fix C as well as what regions. Do you see? Because CM and RM both are variable. Huh? Ah, okay, sorry. So this is called as an indicator function. Okay. Good question. This is an indicator function. So if I pick a point, let's say, if I pick a point here, okay. So this indicator function will be 1 only for R3. Everywhere else it will be 0. Okay. So indicator function for x belonging to R3, it will be equal to 1. Indicator function for x belonging to, let's say, R4 will be equal to 0. So everything else and so on. So for everything else it will be 0. So only one of them it will be 1. So for that entire region I need to fix a value. Is that okay? Yeah, so for the third region, you will look at all the points that are falling in the third region, and you will look at what is the y for that point. You will look at the average, and that will be the C3 for that. So this is only if you know the regions. The question is, we don't even know the regions. So once the regions are known, this is what you will do. Okay, so that is what somebody over the Zoom call told. This is what it is, and this is how we have got. So everybody understands this? Okay, so now the question is, we don't even know the region. So how do I do it? So it turns out that doing that is an NP-hard problem. There is no way you can optimally do this. Okay, so what we will do is we will use greedy approach. So what you will do is you will pick every feature. So there are totally, how many features are there in my training? Like, what are all the features can I split on for a particular regression problems? What are all the features can I fit on? How many dimensions of features I have? All those variables I can split on, right? So basically what we will do is I will pick a J belonging to 1 to D. Okay. Then this is step 1. And step 2, what I will do is I will choose split belonging to split such that. So I will choose a split. When I choose a split, I will have some S such that I will get this R1 of JS is basically this region X such that XJ is less than S. So R2 is J belonging to S such that all the points X such that XJ is so this is less than or equal to, this is greater than S. So like this I will split. Okay, and I will look at for this split I will look at what is the error I will get, right? So what is C1 hat of JS? So this we already saw. This is average. I will explain all of this. You may be confused, but let me just that's why I need to have notes, because there is so many notations here. Yeah, I'll just go over it again. Okay. So my loss JS, let me just write this down and then I'll explain this. Okay, see, so let's come back to the problem. So what we know is that if I know the region, C is good. We know how to do that. It's just the average. Okay, now I don't know how do I split, right? Because there are D different choices. No, I mean for a problem, in the example that I gave you, there were two different problems, right? Two different x1 and x2, two were there. See, why did I split on x1 less than t1? I could have split on x2 less than something, right? So what is the optimal split? Whether I should split with this variable or some other variable, I don't know, right? So the ultimate goal is you want to minimize the total value like this. You want to minimize this quantity. You want to minimize this. So given the regions, I know how to minimize. But if I don't know the regions, how to do? That is the goal. Okay. So for that purpose, what we said is that we will try out on different features one after the other. Whichever gives me the maximum like reduction, maximum like whichever gives me the least value, I will choose that as my split. So that's what I have defined here. So for every j, I'll find a s. I will define an s like this. Okay. And depending upon the s, I will have a split like this. I will get this value. And here I will find out the value of s which minimizes this. Find s to minimize this, right? So do you see? So I will basically try out. I will try out one after the other and see. And for once I fix a value to split, I will try different values or to split. And then I will split that. I will see what's the error I'm getting. Okay, I'll try different values of split, and I will keep trying and see which gives me minimum for one feature. Then I will try for another feature like this. Then whichever gives me the minimum, I will choose that. So that's the greedy approach. So let me give an example so that all of you can understand this. So let's suppose that okay, again, I'm going to give you a trivial example. Suppose there is only one feature x and y is the label that I'm interested to predict. Okay. So let's say these are the points that I have, something like this. Okay. So now I have to try different splits. Okay. So if I put a split here, suppose this is S1. For S1, what should be the value to the left? What am I predicting? So S1 is the point I have chosen to split. What should be the value here? 0, correct? And what should be the value on this side? The average of this. So let's say this is, okay, so you get one error. So this will be L1 S1. So you will get some number. Maybe it's a large value. Let's say it is 25. Do you see? Then you will try to put, you'll keep shifting this S1 and perhaps I will put S2 here. So then what do I get? I have two regions like this, and here is one value and here is another value. Okay. So which of the two do you think will give lower error? So the split 2 will give a lower error, right? So perhaps when you do this computation, you will get 2 of S2. Maybe it will be 12. Okay. And maybe this is the best. So you will go with this. So this is, yeah. Because you see, no, the band. So with the dotted line, the band is much bigger. Yeah, all the things are approximated as one value. So remember, we had all the regions had one value, right? That's why we said we can take average. Okay, so the blue line will look at only the points which are in that region. So there are only 3 points. Here there are only 3 points. The error is minimized here. Is there a question in Zoom? Okay. All right. So this is the idea. So what you will do, let me recap. So you will keep trying for every j, and you will look at the best possible split for that j, and then you will try different j. Whichever j gives the least loss, you will go with that j, and then you will get 2 pieces, and to each piece you will apply this algorithm again. So this is the decision tree. You keep doing it till you reach certain depth. So what if I keep doing till I get only one node? Is there any problem? I will keep doing this. Okay. I will keep splitting. I'll keep splitting. I'll finally finally I'll just do this, and finally when I reach at some point, there is only one node here, one node here, one node here. What's the problem with doing this?
This may lead to overfitting.
Yeah, so this will lead to overfitting. Okay, so basically the complexity here is the depth. Okay, so you don't want to have too much depth. You will stop at some point and you will say, okay, this is the as deep as I will go, because we want to fit overfitting. Okay, so we want to prevent overfitting. So we will look at one more technique towards the end of this lecture, which is on random forest, which also has some way of preventing overfitting. We will look at it towards the end. Okay, so this is basically the decision tree for regression. So do you all follow? It's kind of straightforward. I don't think there is anything really challenging here. I suppose this should be clear to all of you. Okay. All right. So then we will come to classification. Okay. So second one is decision tree for classification. Okay, so the overall goal is always the same. So the idea of splitting the region and trying to come up with the way to split the region, all these things continue to hold. Just that at the final output, instead of having CM, you will have what? So you keep splitting at what do you have? You will just have the prediction. What are you predicting for that entire region? So you will have one label for that region. So what I'm trying to say is that, let's say, take the same example as before. So we had something like this, right? So for each regions, R1, R2, R3, R4, R5, what you will do is you will have one prediction. So I may say this entire region is 1, this entire region is 0, 1, 0, something like this. Okay, I can define, this is the final output in a classification decision tree. Okay, so the question is still there. The question is one, which feature to split on? And the second one is where to split. So any thoughts? Sorry? Yeah, so you are familiar with the idea. So yeah, but if someone who is not familiar with decision tree, what would you do? By the way, if I give the regions, how do I fix? How do I label? If I tell you the regions, how do I label? I'm telling you the regions. Somehow I'm telling you R1, R2, R3, R4, R5. What would your guesses be for those labels? Exactly. So if there is majority of the points are 1, you label as 1. If majority points are 0, you label as 0. Okay. So that's exactly what we will do. So we will look at what is for the kth region. You will look at PMK, right? So basically, what are the number of points that are there in the mth region? And you will look at all the points. So again, indicator is coming. Ith point is actually labeled as K. So you look at this and your prediction. So this is your prediction will be, what will be your prediction? Whichever maximizes this, right? Prediction for the mth region will be argmax of P hat MK. So I just wrote the math for whatever he said. So you look at a region, you see which is the underlying thing with the most points, right? So in general, it's not binary. In general, there could be K different labels. You look at which proportion of labels occur most, and that will be your label guess. Okay. So what is the error? What will be the error in the region M? Other values, wherever you are wrong, right? So that will be 1 minus P hat M, and this is your prediction Km, right? So this is what you predicted. So whatever others are there, that will be your error. That will be your training error. Okay. So now Now coming, so this is when I know the regions. So now if I want to maximize the regions, like I want to find out the regions, you can do what you did before. Essentially, you look at the each variables and try to find out like the probability of error and try to cut, right? The same idea can hold, but what we instead do is we compute. So let me just tell properly. So what we did in regression trees, we looked at the loss, right? And then we tried to find out for which j and which split the loss was minimum, and we went with that. Remember, that's what we did. So now what we will do is we will compute what is called as impurity measure. It's a simple thing, so it's not too complicated, but let me just say we will compute what is called as impurity measure. Okay, so when there we were trying to minimize the loss, here we will try to minimize the impurity measure. Whichever is having the least impurity, we will go with that split. Then that split will give you two regions. Each region, again, you will find out what is the one minimizing the impurity. Can we do this forever? No, because if you do it forever, it will become overfitting. Okay, so there are three different impurity measures. So they are as follows. One is misclassification itself. So basically, you just look at what is the misclassification that is happening. 1 minus p hat m km. Okay, this is one. The second one is called as Gini index, which is and the third one is called as entropy. I will explain this and you'll get better sense of what is happening, but let me just first write it. Okay, so see, the idea is as follows. Okay, so suppose so let me try to explain the idea behind impurity measure. Okay, so let us say there are two ways in which I can split. Okay, so let's look at that. So one example. So suppose I have a split. So split 1 gives me this. So I get two different regions. In one region, 3 of them are marked as blue and 1 of them is marked as red. In the other region, 3 of them are marked as blue and 1 of them is marked as 3 of them is marked as red and 1 of them is marked as blue. Okay, so this is split 1. In split 2, I have so what is the, okay, so there are these two splits. So first of all, in this split, what is the label here for the first box? Blue, right? This is going to be labeled as blue and this is going to be labeled as red, correct? So what is the total error? What is the total error I am making on this? So 2 points are wrong out of 8, 2 over 8, correct? So the total error is 2 over 8. Okay. What about split 2? What is the label here? Blue, right? What about this? It could be blue or red. So let us pick it as red. So then total error is for this thing again 2 over 8. Yes. So which of the two is preferable? That is the question. which among the two you think we should do? See, if I use just the error rate, okay, for both these things, error rate is same. Okay, and I have how is split 1 generated? It was generated on one feature. Split 2 was generated on some other feature. Okay, so which of the two do you think we should prefer? So how many of you feel split 1? So can you raise your hands if you feel split 1? Okay, so can one of you tell why you think split 1 is better? How about split 2? Anybody who thinks split 2 is better? Okay, a few of you. Okay, can one of you tell why you think split 2 is better? Yeah. So the idea is, see, once you have done split 2, as he says, perhaps then when you look at this region, I may get a split like this. And then I will be able to perfectly classify everybody. Okay, so you want to minimize this impurity, under quotes, this uncertainty you want to minimize. So this is the idea that is capturing the impurity. Do you see? So in some sense, split 1 is said to be impure because there is some kind of, it's not, one region is not completely sorted. See, if you want to, let's say, do a lot of things, you divide it into a way, you finish one thing completely, then you start the other piece, right? So the same idea here, you want to finish one portion completely and then come to this. Okay, so essentially this is what, so if I use just misclassification, if I just use misclassification, they cannot tell the difference between the two. Do you see that? If I use just the idea of probability of error, both these things give the same probability of error. I will not be able to distinguish them. How many of you understood the example here? Please raise your hands if you have understood. Okay. Okay, good. So you have, so basically probability of error is not enough because you will get the same probability of error here. But if you use instead these measures, this or this, okay, so what happens is it will show a higher value for this. This will be high and this will be low. Okay, so that's the difference. So you can actually compute and see, and you can do it. The formula is there and we can try and compute and see. Okay, the idea is what I wanted to convey. So this is what it is. So like, look at this, for example. So let's look at Gini index, right? So if PMK is either 0 or 1, what is the value here in the summation? 0, right? If PMK is either 0 or 1, this summation term will be 0. Okay, so that way many terms, if many regions are having that property, they will all be 0. So that's how it is encouraging you to kind of have pure nodes. Okay, so this is the impurity, and essentially that's what it is. So depending upon the regions, you will compute this NL times Q RL plus NR times Q RR. So you will look at the impurity in the left, look at the impurity in the right, multiply it with the number of points in left plus number of point in right. So this will give you one value. Okay, so this is for one split.
There is a question from online audience.
Yeah.
What is the significance of Gini index? What is the intuition behind it?
Yeah, so let me again repeat because I did explain that, but okay, so see, we want to minimize the impurity. Okay, so Gini index is what we want to minimize. So Gini index is flashed on your screen. Okay, so if you look at this, you are summing over all the different k possible values, you are summing over. Okay, so you would ideally want regions where PMK is either 0 or 1. Because if PMK is 0, then this term will be 0. And if PMK is 1, then this term will be 0. Okay, so you want to minimize that. So you want regions which are of this form, which are of this form, the split 2. It tries to pick regions of split 2 form. Okay, so the idea is very simple. What you do is you try every feature one after the other, look at which feature minimizes the impurity, choose that feature, And amongst all feature, whichever has the lower scores, you start with that first. The same thing as you did for regression tree. Okay. So this is essentially what is regression decision tree for classification. Okay. Again, I'm not going to ask you to implement this from scratch. So you can try out the libraries. Perhaps they have some assignment. Yeah. So we can just run that and see. Okay. So this is related to trees. So then coming back to random forests. Okay. So before that, we need to talk about what is called as bootstraps. Sorry. Okay. So let me just say, right. So what is the thing you want to do? You want to come up with the regions and you want to come up with the values for the regions. Okay, that's what you would like to do. So if I give you the regions coming up with the value, you said what we will do is what is the most points under that region and come up with that. Okay, now the question is what regions to come up with. Okay, so what you will do is you will try with every feature one after the other, one after the other. Each feature you will look at a split. You will look at the split and you will look at what is the impurity of the region. Okay, so NL times QRL plus NR times QRL is an impurity of that, of the split. You try for every split, take the one which is minimum. Okay, then you will look across all the features and see which has the minimum. That is your first split. Then you continue like this. Same thing that you did for regression. Okay, so then coming up next topic is what is called as random forests. So any other questions here? Okay. Yeah. No, the total number of blue data points is 4. Oh, okay. I see what you're saying. So let's fix that. Yeah, I see what you're saying. I think I just hastily put this together. What would be a better example? You remove these two crosses from this and make it red. I need to have the same error. Three red and one blue. Let me see. No, you need to, I need to show pure node. Okay. Huh? Okay, so maybe I will put yeah, one here. Let's see. I don't know. I'm just now trying to improvise, but I hope the idea is clear to you. Yeah, but anyway, it's the instructor's job to somehow fix bad examples. Maybe. Okay. So this is correct, and I need to have 4 reds, and let's see. Okay, is that okay? Is that better now? So totally 10 points, 4, 4, 5, 6. Yeah, is it okay? Four out of 10. Error, both errors are 4 out of 10. Okay. All right. So you understand. So there is a way to do it so that you get same error and all that. Okay. But the point is you want to get pure node. Okay, so there is a way to split this. I just was too casual. I didn't see properly. But it's a good point. You should compare apple and oranges. I cannot take completely different setting and say, yeah, but there are examples where you can see this. Perhaps there is one over in this. Yeah, that since she has asked, let's look at this. Yeah, this is an example. So again, this is from that book. So so let's take this region. So we will have 4 different colors. And then okay, so this is the arrangement. Now there are 2 ways I can split. First, I can split over here. Okay, and then I can split like this and like this. This is one way. Or I can split like this, and then maybe I will show it in black. Okay, which of the 2 split is better? First one, right? And there you can actually compute the impurity index that will have a lower impurity. Okay, so this is a proper example from one of these textbooks. Okay. All right. So so now yeah, so now let's understand the idea of boosting, and then we will see random forests. In fact, before boosting, let's talk about Bootstrap. Okay, so so let's look at. So I have I want to estimate coin tosses. I want to estimate the heads. What is the probability of getting heads, right? So what I do is I will do zi's, which goes from, let's say, 1 to 100, right? And I want to estimate the mean mu. So mu hat. So my claim is there are different ways you can do. So for example, mu hat could be just the sum of first 10, or mu hat 2. This is mu hat 1. Mu hat 2 could be, I can take 50, or I can have mu hat, which is just the sum of everything. So which of the 3 is better? What do you think? Which of the 3 is better? Huh? Third one. Why? But why summing up everything is good? Okay, so what he's saying is, like, suppose the first 10 are positive, but mostly the data is negative. So if you take only first 10, so what is the idea of this? So what are you trying to say? Which one has, what's the keyword here? What's the probabilistic statement to make here?
Most representative of the data.
Representative of data is also true. Taking more is better representation. But what I am looking at is what is the variance of each of these estimators?
Okay.
What is the variance of mu hat? Which one has the highest variance, right? So,
yeah.
So if Zi, if expectation of Zi is mu I, and if variance of Zi is sigma squared, what is the variance for each of these 3 estimators? Have you seen this kind of calculations in your yesterday's class? Can someone tell me what's the variance of, what's the mean of, first of all, what is expected value of mu1 hat, for example? What is that equal to? So let me just make some small corrections. Since these are coming from the same sample, there is no question of mu I, right? So it's just mu. Okay, so what is expected value of mu1 hat? The mu1 is, remembered, by taking 10 samples, I have got some value. So what is the expected value of mu1 hat? Yeah?
N by 10 mu.
Mu. So the online audience is saying mu, but what about the people here? Is it mu or something else?
Let's see.
It's mu, right? Okay. So this is expected value of mu1. In fact, expected value of mu2 hat is also mu1. Expected value of mu hat is also mu. Okay. All these things are fine, right? So now, what about variance of mu1 hat? Does anyone know how to do this? Yes. So you can check some textbooks. It's sigma squared by 10.
Squared by 100.
Yeah. And variance of mu2 hat is actually sigma squared by 50. And variance of mu hat is sigma squared by 100. Okay, in general, it is sigma squared by n. So this is the variance of the estimator mu hat. Okay, and the standard deviation is sigma by square root n. So now you were saying, right? So low 10, high, that example is more concretely, you can say the variance is low. Lower variance is always better. Okay. So that's easy, right? I mean, you want to predict some value, lower is always better, clearly. So in fact, you know, many real world applications of this standard error is particularly very useful. So what you will do is you will look at mu hat minus 2 standard error, comma mu hat plus 2 standard error. With high probability, you can say for sure that your true parameter lies between this. Okay. So with high probability, this is true. Your actual mu with belongs to this with high probability. So when you look at, for example, if you look at all these randomized control trials, vaccine efficacy, right? They say 67%. They always tell you what is the left hand side and the right hand side. So this is coming from this. Okay, so 2 standard errors, left and right. Is it 2 or 1.96? Yeah, so it's fine. So this is what, so yeah, so the idea is if you have multiple samples, multiple estimations, it's always better. Okay, so the same idea, let's suppose that, so let's try to extend this idea for predictions, like for learning problems. So yeah, so before that, let's talk about bootstrapping. Okay, so now the bootstrapping idea is as follows. So you have n training samples. So you have data which is x1, x2, xn. Okay. So from this n training samples, you will generate b different samples. So 1, 2, 3, all the way till b different samples. So how we will generate is you will pick one of these samples at random, okay, and you will add it. So the procedure is pick one of d at random, okay, and add it to my set. So like that you will repeat. Okay, so what can happen? I can add multiple items, same item I can repeatedly add, and there could be some items that I completely miss. Do you see how I'm generating these samples? So this will be my sample, let's say d tilde 1, d tilde 2, d tilde 3. See, the idea is it would have been nice if you had b different samples which are independent. Okay, but independence That means you need to collect more data, but you don't have that much data. So you simply sample your whatever data you have, you sample it again and again. Do you see? So that is the goal. So you don't have independent data, but you resample and get as many data as possible. Then what you will do is you will look at whatever estimate I want to make. I will make mu hat of D1 tilde, similarly mu hat of D2 tilde. Like this you will do, and dB tilde. There will be different values. And now what I can say is that I will take then average among this. Okay, so I will take average amongst all of this. So the idea is by doing this, you are able to get the same effect as you would have got if you had actually independent data. Okay, so why do having that is better? Because when you have more data, you have lower variance. Okay, so this is the idea of bootstrapping. Okay. So maybe if you have time, you can actually do one thing. So what you can do is you can simulate this. You generate 1000 coin tosses. From the 1000 coin tosses, you generate subsample it and generate different training sets. Okay, and then try to compute what is the probability of head you get in each of that, and try to plot the histogram. That's one. So maybe I can just say optional lab. Okay, so what is that? So one is so you have D, which is 1000 coin tosses. Okay, then second is bootstrap. Let's say 1000 samples, and generate histogram. Histogram of what? Mu hat di. Okay, this is one. Second, it could be you actually have 1000 so independent samples. You have 1000 samples. Okay, and second one is you have 1000 such samples. 1000 of. Do you see what I'm trying to say? Such samples. One is completely independent case, one is bootstrap case. You try to look at the histogram, they will look quite similar. Okay, so even though you don't have a lot of data, you are just generating data from just keep on sampling your existing data. You just do it and look at the histogram, there will be quite a lot of similarity. So this is an optional lab you can try. So at the end of this session, I'll be around. So if you have any questions, we can just simulate and see in your PCs. Okay. All right, so this is the bootstrap. So what is it that you do in case of learning? So what you do is this. So let's say random forests. So what is the algorithm? So first step is so there are totally D features, right? So you have D features. So you have your original training has xi1 all the way till xid, right? So from this, you will first choose M features at random. Okay, so that once you choose, you will get some M features. Okay, and then from the after that, and generate bootstrap samples. So the procedure is you have D features, you choose M of them. So M is typically chosen to be square root of D. So you look at a small subset of features. Okay, and then from your original training, you have got some reduction. Now using that sample, you generate multiple copies, bootstrap it. So that will give you one data sample B1. So like that, you get B2, B3, all the way till some BK. Okay. And on each of this, you will use decision trees. So there will be a decision tree here, decision tree 1, decision tree 2, decision tree 3, like this, decision tree 4, decision tree K. Okay. So you do this. Now, how do you aggregate it? How do you aggregate? Let's say if you want to do classification, how do you aggregate? And if you want to do regression, how do you aggregate? For classification, what will you do? See, I've got k different decision trees. I need to aggregate. So what will I do? I will just take my training sample, pass it through every decision tree, and I will see what each decision tree is telling me to do. So whichever the majority agrees upon, I will use that as my label. Okay, so for classification, I will do majority voting. For regression, what will I do? Sorry? Yeah, so regression, you will take average. Okay, so this is the random forest algorithm. Okay, so why did we, so what is the idea of taking B1 to BK? Have you seen already in the course bias variance trade-off? Have they done this? Yeah, okay. So there will be actually a specific discussion on bias and variance. Okay, so decision tree, if I am overfitting, what it means is that the bias is low because I can fit anything. If I go deep enough, I can fit anything. So if I given infinite data, it will actually fit properly. So bias is low, but the variance is high. Okay, depending upon what sample I give, it will behave one way or the other. Okay, so by taking different bootstrap samples, what am I getting? I'm getting lower variance, right? I explained how that happens, right? So whenever you have this kind of square root of n term comes in, right? So the variance reduces. When I take different bootstrap samples, there will be some term like this which brings down the variance. Okay, so that's the essential idea behind random forests. All right, so this is essentially the idea behind this. So I'm kind of done. So if what we will do is we can spend some time discussing something else, or if you wish, we can talk a bit. Maybe I will tell little bit about convolutional neural networks, little bit. It's not part of your labs, but you can actually do it if you wish. Okay, so we can do that. Or if there are any questions so far in whatever we have covered till now, you can do that. You can ask me that. So one of the two. Yeah. Yeah, so bootstrapping is the like, so did you understand bootstrapping, how it works? So there are n data point. So with probability 1 over n, I will pick a data point, put it in my bag. Again, I will pick, right? So same, I may get the same copy again, I may not get, yeah. But this is kind of the only provable way. So people have shown some guarantees by doing this. It's not as good as having independent data, but it is kind of good enough. Yeah, any other questions? Any questions in the audience? Okay, so let me just talk about convolution operation. Okay, since it's kind of very practical for machine vision, computer vision. So let's just try to touch upon that, and we will stop. So we started at 2 o'clock, right? So till another 15 minutes to go. So I will briefly tell, and then we will stop. Okay, so this is a this convolution. It's used for image computer vision applications, or image with images. Like if there are a lot of images, you may want to use convolution operation. Okay, so what is the point? So let's suppose that there is a image of a car. Okay, there is a car like this, and it is going in a let's say on a road which is let's say some, and then there is a lot of background like this which is blue. There is a car it's going on a road and a lot of background blue. Okay, so so this is my input to my learning algorithm. So the total number of pixels are like width into height, right? So if you have time, if it's a movie, then there will be a time dimension as well. Okay, so now so basically now consider an operation like this. So imagine that there is a 3x3 grid like this, okay, which is -1 -1 -1 -1 8 -1 -1 -1. So some matrix like this. What I will do is, so let's say this is my image, and let's see. So this is my image, and this is called as a filter. Okay, so this thing that I have written here. This guy is called as a convolutional filter. Okay, so I will take this image, I will put it on top of this. Perhaps it's even smaller, right? Because the image is much bigger, whereas the filter is very small. Okay, so you have the image, and then you have the filter. You overlap it, okay, and you keep moving this one at a time like this. Okay, then you go down. Okay, like this, you keep moving it. So what it does is, so what is the operation you are doing? So the image is like this, right? So when it is blue, it is of one color. Let's say it is something like 5 5 5. All these blue I am representing by 5. I mean, typically there is RGB, different pixel values are there for RGB, but assuming that there is only a single number, it's going to be 555 555, something like that. All the regions which are blue will have the same value. What it is, I don't know, but some value it will have. So if I overlap over this, what I will do is I will multiply term by term whatever comes underneath that, right? So that 1 -1 -1 -1, that over this I will overlap. Whatever term comes under that, I will multiply and add. So what will I get? So I will get 5 into -1 plus 5 into -1 plus 5 into -1 plus 5 into -1 plus 5 into 8 plus 5 into -1, like this. So what will it do if I keep multiplying like this? What is the value I get? Anybody? 0, right? So you'll get a value 0. So as you move that filter throughout the image, I will get 1 1 1 1 value. So I will take an image and I will generate a new image. Okay. So if the image was of that car, what will I end up getting? I will get a whole bunch of zeros wherever all the pixels are same. So essentially what I will get is edge. I will get the edge of the car, right? So I will have only the edge. And I will have the edge of the road, something like this. Do you see why that happens? Okay, so you will get from the original image, you are only getting edge. So this convolution operation with this particular filter gave me this. But if I try something else, some other filter, I may get something else. Okay, so this idea is this. So you take your original image, try different filters. What values to put in the filter? How will you find out? How will I put, how did I randomly chose this value, but how do I engineer these values? Sorry? You use gradient descent to find out, right? You don't worry about it. You just decide the size. Let the gradient descent figure out what values best to put. So it will figure out by doing gradient descent. You will do forward propagation. Forward propagation is just multiplying and passing it to the future layer. At some point, loss will be computed. And using that loss, you will get what values to put so as to get the best performance, right? That's what we have been doing even in the previous thing. How did we choose the W's? Did you engineer it? We did gradient descent, right? So you start with a random value, you do gradient descent and choose that W properly. Okay, so this is the convolutional neural network. So This is the convolution operation. So again, there is something called as forward pass. Forward pass is very clear. You just multiply and get a value, pass it, right? You generate that for the entire image, you get one more image. Backward pass is computing the gradient. So you need to compute the gradient with respect to the weights. Okay, this unfortunately, due to lack of time, we will not be able to do. Okay, so yeah, so this is the backward pass. So you can actually hand code and implement this and get good performance even with this, right? So this you can try. So you just try to figure out, read up on the internet. There will be good resources on how to do this and try it out. It's a very interesting exercise. Okay, so that's about it. So let's just stop here, and we'll take a break for about half an hour. Right, half an hour we'll take a break, and then we will start the lab session. So he will describe what to do in addition to what I have already told you to do. Okay, and I will be around. So if you want some of my help, you can call me. All right. Okay, so let's take a half an hour break and we will reconvene 10 minutes to 4. Okay, all right. So you can stop that.